Hello, my name is Jonathan Bohren with Honeybee Robotics, and along with two colleagues of mine, Steve Hart at TRACLabs and Dave Coleman at PickNik Robotics, we are going to present on some recent independent work integrating CFS, NASA's core flight system, with ROS, the robot operating system, and why the flight software community should be interested in leveraging work done in the ROS ecosystem for space robotics. As you'll see, while both TRACLabs and Honeybee have built effective prototype bridges from CFS to ROS2 and ROS1 respectively, each of these somewhat similar approaches has limitations which make them the wrong way to leverage ROS for space applications in the long term. This also isn't the first time that CFS and ROS have been used together. For example, previous efforts by JAXA take a very different approach from what we presented here, and we encourage you to take a look at that work as well. We'll start with some introductions for our three companies, and each of us will then take turns for the following three segments. Dave Coleman, CEO and roboticist at PickNik Robotics, will first give a brief overview of ROS, describe some of the open source components on which PickNik focuses, and then give some highlights of where ROS is already being used in aerospace systems. Then Steve Hart, senior scientist at TRACLabs, will present their recent work in integrating CFS and ROS2, along with an example test case, and describe the limitations of that approach, along with the future work under their next Phase 2 SBIR grant. Finally, I'll return to present our own work at Honeybee integrating CFS with ROS1, discuss the approach's limitations, and then pose a challenge to the CFS community to embrace some open standards which would reduce the complexity of integrating CFS with ROS systems in the near term, and other arbitrary middleware interfaces in the future. Honeybee Robotics was founded in 1983 in New York City and is now a wholly owned subsidiary of Ensign Bigfoot Industries, operating in the space, aerospace, defense, and mining sectors. We primarily offer spacecraft motion control and robotic systems products and provide design, manufacturing, integration, test, and operation services. Honeybee is ISO 9001 and AS 9100 certified and has about 250 employees across 3 offices in Brooklyn, New York, Altadena, California, and our headquarters in Longmont, Colorado.
Hi, my name is Stephen Hart, and I'm a research scientist at TRACLabs located in Houston. TRACLabs is a small company that focuses on pushing the state-of-the-art of AI and robotics for government and industry. Our robotics group has a long history of support for NASA systems, mostly at JSD and Ames, including Robonaut, Valkyrie, and Astrobe. We primarily develop ROS-based application software to better support the operation of remote robots for activities such as multi-robot coordination, station caretaking, OSAM, and habitat construction. Relevant to today's discussion, we are currently investigating ways to bridge the NASA CFS software with ROS to help support the next generation of flight systems.
Hey, yes, I am Dave Coleman. I'm the CEO, founder here at PickNik, and have a background in robotics. And what we do is work with a ton of companies on best using open source robotics software and customizing and integrating it for all sorts of hard robotic problems, particularly around robot arms. Most recently, we've been working on an SBIR Phase 2 with NASA. And with that, I want to talk about why ROS, what's the advantages of using this in space, what is ROS? So first, there's a lot of applications in ROS. One of the biggest ones is Movelt, and it's relevant because that's our main software at PickNik that we provide to customers, and it does all sorts of advanced motion planning, manipulation, grasping, and controls for robot arms. It's used by NASA. It's been used by a lot of different companies, but it's part of this ecosystem called the Robot Operating System, and it's been widely successful since 2007 when it began at Stanford. And it is a loosely federated collection of software packages, kind of like CFS, but a lot of differences too. It includes a lot of how should you build your software and how should you organize it, and a lot of just pre-built things that are commonly needed in robot applications. It's independent of language, so you can see in this list here, it's been used primarily C++ and Python and C, but also a ton of other ones too. It's distributed, meaning that it's a middleware that communicates between different processes. And one of the favorite things, of course, it's free and open source. And so it's maintained the core by Open Robotics and a number of contributors in the open source community. Open Robotics has gotten a lot of funding from NASA, DARPA, other government agencies. So they've been used a lot in government programs as well. And in that core, you get visualizers for robotics, tools for debugging, introspection, all sorts of stuff. And on top of that, you have all these academic universities who've published amazing open source code on top of ROS, a lot of companies, including PickNik Robotics, publish its open source software on top of ROS. And it's also been used a lot in space arms. These all use ROS and move it to varying degrees. We have the Valkyrie, Robonaut 2. Most recently, Githai has been doing the space station experiments. Motive Space Systems uses ROS, and so does Tethers Unlimited. In terms of ROS spaceflight heritage, the Astrobee currently is in the station running ROS internally, both for message passing and for simulation. And in a future program, Viper, to the south pole of the moon, will also be running ROS 2.0. There have been many challenges. So Terry Fong published papers in 2013 talking about how ROS maybe is not ideal for flight systems, only for prototyping. And so JSC has used ROS a ton for their research and prototyping. However, there is now, 10 years later, a big movement to actually create a space-safe version of ROS, a flight-safe version. And it's being spearheaded by Blue Origin. They're converting ROS to be space qualifiable. And they're working with a bunch of NASA centers in doing this. And so what will be space ROS, it'll be continuously qualified and have a lot of the compliance artifacts necessary to be used and tested safely. And with that, I will hand over discussions on CFS and ROS to Stephen.
Hi, Steve here again, now to talk about TRACLabs' efforts in building a ROS to CFS bridge. While TRACLabs primarily has developed ground-based software for full or semi-autonomous robot systems, we recognize that there is a large gap between what is possible in the laboratory or non-flight scenarios and what is possible in more limited NASA mission contexts. Noting that the strengths of flight software systems such as CFS are complementary to the strengths of large-scale open-source domain-agnostic development efforts such as ROS, however, provides a unique opportunity to figure out how the strengths of each can be leveraged to better support future NASA missions. To these ends, we have recently explored how and in what contexts the DDS-based ROS2 can be integrated with CFS. This has been joint work conducted with Andrew Harris and Chris Kruppiarts from the Applied Physics Library at Johns Hopkins University and funded through the NASA STTR program. It is our hope that examining how these systems fit together, robot systems developers can benefit from integrating the vast array of software libraries for autonomy, perception, and development available from ROS with the safety and reliability benefits of CFS, ultimately leading to faster development times, increased software reuse across missions, and the cultivation of a larger community of developers using shared tools and practices. For our investigation, we primarily focused on two approaches. In the first, we examined how ROS2 applications can be run as part of the ground system, communicating with the flight system using the standard CFS telemetry output and command ingest applications, commonly referred to as TO and CI. This approach is beneficial because it is both straightforward and alleviates the need for the flight certification of ROS components, keeping them out of safety-critical pathways. It also allows ground operators to both visualize and interact with ROS-based components in standard ways, using development tools such as RViz that have been such a boon to the robotics development community in recent years. The disadvantage of pushing ROS to the ground system only, however, is that this limits the capabilities of the flight system itself and induces latencies in the loop that could be significant depending on the mission, and that will have to be managed or designed around. The second approach, which we will not discuss here in detail, is to allow ROS2 applications to be run on the flight hardware, communicating with the flight software using a CFS DDS software bus network or SBN plugin. As the primary communication protocol of ROS2 is DDS, such an SBN plugin would allow ROS message data to be placed on the CFS software bus as if the messages were part of the same process and vice versa. While such an SBN DDS plugin has been developed, though not by us, we haven't yet performed a full investigation of this integration path but hope to in the near future. Going back to the ground system approach, we developed a proof-of-concept bridge that bootstrapped off of the off-the-shelf CFS ground system Python application that comes with the standard CFS installation available from Goddard. This ground system application communicates with UDP-based TO and CI CFS applications and automatically populates some desktop user interfaces that allow ground operators to view telemetry data and send commands. Our proof-of-concept bridge wrapped this application as a Python-based ROS2 node that automatically translates between CFS and ROS2 message formats. As CFS messages are defined in C structs that require strict typing and byte ordering, the primary challenge lies in how these messages can be repurposed into ROS2 message formats that are compiled from looser ASCII file definitions. Fortunately, the Goddard ground system application provided an intermediary message definition format using CSV for telemetry messages and pickled Python dictionaries for command messages. While the conversion between C headers and these formats is done manually, our future work will investigate more automatic conversion processes. Nevertheless, having these intermediary standards allowed us to easily write some general-purpose message conversion utilities, allowing us to create ROS message equivalents to all telemetry and command messages that have been specified in these configuration files. At runtime, our bridge converts messages one way or the other, utilizing Python introspection and the parsing utilities developed to create the ROS2 message equivalents. The process is fully automatic, relying only on the ground system application CSV and pickle configuration files, and a choice of naming convention standards we have imposed. This slide shows an example of a standard telemetry message as defined in the ground system application CSV format and the automatically generated ROS2 message equivalent. Similarly, here we see a command message defined as a pickled Python dictionary and the generated ROS2 equivalent. Note that our conversion utility is a ROS2 node that automatically crawls the file system to allow command messages to hierarchically utilize further message information necessary for modular parameterization, which CFS takes advantage of. This video shows a simple proof of concept of our ROS2-CFS bridge in which a ground operator uses the standard ROS RQT user interface to send a command message, which is then translated into a CFS message that enables telemetry to be broadcast from the CFS TO UDP application. Once enabled, the telemetry, which is then translated into a ROS message, can also be viewed in the RQT application. Finally, we set up a simple closed-loop demo utilizing our bridge to control, from the ground system, a simulated SSRMS robot. To set this demonstration up, we created a simple CFS application that served as the 7 degree of freedom robot, where the current joint state of the robot is published as a telemetry message at 1 Hz, and a command input accepts joint goals. These goals are processed by a simple PDE controller in the CFS robot application that assumes perfect commanding of the robot. To set the goal position of the robot arm, we use the standard joint state publisher ROS slider application and are able to see the current state of the robot in RViz updated at the 1 Hz rate, coming from telemetry we get from the CFS system and translated back into ROS. This example illustrates one key challenge in creating a bridge between ROS2 and CFS. While the data itself can be transmitted and received using the TO and CI applications, for example, and utilities can be created to translate between the message formats of each system will more than likely have their own message definition formats. For example, in ROS, there is a standard joint state message definition for collecting aggregate joint position data for a given robot. In CFS, there is no such standard, and we had to create a simple C-struct with a float array for our demonstration. As such, there needs to be some process that translates between these two formats, and in our setup, this is done after the CFS messages have been translated into an equivalent automatically generated ROS message utilizing a custom joint state conversion ROS node. This process is necessary in both directions, as ROS joint state command data coming from the slider UI must be converted into a CFS-generated ROS message before then being converted into the UDP packet that can be interpreted by the CI/CFS application. While such conversion utilities were created for this proof of concept, this complexity represents arguably the key challenge when trying to integrate ROS and CFS, or any other flight software system for that matter, as there is no agreed upon ground truth specifying data structures that may be of use across systems, missions, or domains. Based on our exploration with the above proof of concept, we've recently been awarded a 2-year Phase 2 NASA STTR contract to pursue these ideas further. Our plan for this effort is to generalize the tools we have developed, possibly allowing us to bridge ROS2 to other flight software systems such as F', integrate the DDS-SBN application we discussed earlier, and to create a toolkit of utilities that flight systems developers can draw upon to support message conversion, time synchronization, logging, and event management. One key effort will be to investigate the efficacy of a common command dictionary that can be shared between systems and that developers can leverage effectively. And with that, I'll pass it on to John. Thank you for your time.
Honeybee has a long history of using ROS for robotics R&D, and over the past year, we've developed a ROS-CFS Bridge to support an early-stage flight robotics development project. This system needed to be designed around high-tier components and software, but it benefited from infrastructure and algorithms already present in ROS, since it included multi-agent robotic manipulation. Our approach to interfacing CFS with ROS makes 3 main assumptions. First, CFS message definitions are stored on disk as C header files. Second, the definitions may be volatile during development. And third, the sources for those definitions are always available to the ROS build system. Integrating CFS and ROS messaging presents a challenge because the two middlewares have different workflows and representational constraints. First, ROS message structures are only defined with a platform-independent interface definition language, while there are numerous in-house systems for defining CFS messages. While some of these systems are used more frequently than others, there is no standard interface definition system embraced by the CFS community. Second, ROS messages are serialized for transmission at lower-level transports like TCP and UDP, while CFS directly uses CCSDS space packet protocol messages at the application layer. This simplifies the CFS middleware and allows a one-to-one correspondence between messages and packets, but it imposes additional restrictions. CFS messages are not bit portable between platforms, and there are features of the ROS ideal which cannot be utilized in CFS messages, such as variable length strings and arrays. This means that all message vector fields must be bounded at compile time, and poses problems for large messages which would normally be partitioned into multiple packets like trajectory commands or camera image data. In addition to the assumptions about the development environment, we also imposed 4 top-level requirements for the CFS-ROS integration in order to make the tool useful in practice. Neither CFS message IDs nor command codes shall be replicated manually to minimize bookkeeping overhead and avoid transcription errors. ROS message definition shall be generated ephemerally by the ROS build system to avoid using out-of-date messages. CFS messages relayed into a ROS system shall support all normal ROS introspection tools, and relevant constants and enumerations defined in CFS headers should be stored in the generated ROS messages for easy access. The CFS-ROS interface comprises 2 components, PyCFS and ROS-CFS. PyCFS is a standalone Python tool for processing CFS-C headers and interfacing with TOLab and CILab, while ROS-CF is a pair of ROS packages, CFS Message Gen and CFS Bridge, which use PyCFS to both generate equivalent ROS ideal messages at compile time and to translate between CCSDS space packets and ROS messages at runtime, respectively. Both of these components have been published online under an open source license on GitHub. Whenever CFS messages change, building a ROS workspace will automatically regenerate appropriate ROS message definitions. Given a CFS bundle, which includes the CFS core and applications, a thin ROS package can be created which identifies that CFS bundle, mission name, and target name, along with a number of declaration patterns which match message structures and constants. When the ROS workspace is rebuilt, this thin ROS package uses facilities in CFS Message Gen, including PyCFS, to generate corresponding ROS message definitions and stores the parsed headers in a cache that can quickly be loaded in future runs. Finally, the normal ROS message generation process generates language bindings from the ROS message definitions. It's important to note that these generated messages are portable across CFS targets, as long as standard build types are used. Shown here is an example exposing CFS message types to the ROS build system in a standard CMake build file. This would be the only file in a ROS CFS interface package and uses the add CFS messages macro to generate ROS messages from CFS headers. It identifies the CFS bundle and specifies patterns for structures and constants to be translated. On the right are examples of the results, including all constants that match the given patterns in a special constants ROS IDL file, and ROS messages for each CFS space packet structure. At runtime, one or more CFS bridge nodes can be launched, which identify a given bundle, mission, and target. Each CFS bridge node then determines the PyCFS cache and the target-specific encoding to translate ROS messages to CFS space packets. For each command message ID and command code, a ROS subscriber is instantiated, and for each telemetry message ID, a ROS publisher is instantiated. Each of these is bound to the appropriate UDP sockets to communicate with a CFS executable running CILab and TOLab on the CFS side of the bridge. This CFS executable can then operate as a gateway to other CFS executables via the software bus network application. On the ROS side of the bridge, any ROS node can communicate using the generated ROS messages normally. This implementation has several limitations. First, there's no single source of truth for ICDs. Header parsing is fragile, and headers can't be statically processed. This is really in any situation in which you're parsing C headers for purposes of doing anything other than building an executable, you're probably doing something wrong. Second, the bridge is not portable between targets. Translation to binary representations is target-specific because the binary representation is unpacked, and it depends on the target platform. Third, messages are restricted to what CCSDS, Space Packet Protocol messages, can represent. This includes variable-sized data types like arrays and strings, which are not supported, and additional protocol layers are needed to leverage multi-part messages, which are not currently supported by CFS. Finally, this bridge was only implemented to work with the CI-Lab and TO-Lab UDP protocols, and in the real mission they would need to be replaced with something else. Several of these issues are unavoidable due to the manual specification of CFS messages and C header files and the utilization of CCSDS space packets at the application layer in CFS. However, CCSDS 876.0b1 defines a standard for spacecraft interface definition. A possible approach to address these portability and robustness issues is to have the CFS community embrace the CCSDS electronic datasheet standard for space system interface definition. A prototype implementation of CFS which leverages this standard has already been published by Joseph Hickey on GitHub. In addition to generating C headers from interface definition files, this work addresses several other CFS development pain points. The NASA CFS EDS toolchain could easily be extended to generate ROS messages from EDS XML files instead of using CFS C headers as the input. When building a CFS bundle, the EDS tool would use a ROS plugin to generate CFS C headers and ROS messages simultaneously. These ROS messages would subsequently be used by the ROS build system to generate language bindings, as they would be normally. EDS would simplify the integration of CFS systems with ROS, and other middleware systems could be integrated with similar ease. ROS message definitions would be more portable between CFS targets, and EDS would enable description of variable-length messages via containers. However, support for this in CFS would still need to be implemented. We'd like to encourage the CFS community to seriously consider baselining the EDS workflow to make interfacing with the CFS middleware more robust as software complexity scales for these in-space robotics applications. Thank you for your attention, and we hope this has both shown how ROS can be leveraged to add capabilities to CFS-based systems, and how there's still a lot of work to be done to do it in a way that maximizes performance and safety assurance while minimizing maintenance overhead and interface bookkeeping. Please don't hesitate to reach out to any of us for follow-up questions or discussions, and thanks again.